Okay. Hooray! So we'll start over as if this is the beginning of class. All right, so first chapter of BGP, talk about why do we care, what is BGP for. So the first thing to talk about is enterprise connectivity, okay? So um, here we're talking about outbound connectivity. Well, and it says in the rare case. Well, in the rare case that we only need outbound connectivity, that's just about never. Okay, we usually need both inbound and outbound. Okay, so we have two-way connectivity um, to the outside world. Okay, then we might have edge device redundancy so that we have more than one edge device that's connecting everything up. Okay, link redundancy and even ISP redundancy. Okay, so we've got one link to one ISP, one link per ISP for two ISPs, um, two links, right? Two links. So then that kind of brings us to our interior gateway protocol. That's the routing protocol inside our autonomous system, like EIGRP or OSPF. All right. But outside of our autonomous system, we have an exterior gateway protocol. That's what's used to route stuff between autonomous systems. Well, and that is BGP, or Border Gateway Protocol. So that's our exterior gateway protocol, also called an interdomain routing protocol. Okay, so this is a path vector routing protocol. So we have some elements of a distance vector. However, we have additional path attributes, including the exact path from start to finish. All right. The first thing we need to understand in this context is what is an autonomous system. All right, so there's kind of two meanings here. One of them is just a set of routers under a single technical administration. All right, so that's our autonomous system, and then we use our exterior gateway protocol to route packets to other autonomous systems. All right, so with regard to BGP, we have BGP version 4. All right. BGP version 4 is able to do IPv6. It didn't require a new BGP version, kind of like EIGRP was able to be updated without a full rewrite. All right. Now, the technical definition of an autonomous system is pretty similar to what we just said. A set of routers under a single technical administration using an interior gateway protocol, and common metrics to determine how to route packets within the autonomous system, and using an inner autonomous system routing protocol to go to other autonomous systems. All right. So in order to do that, we use BGP version 4. Okay, and then BGP version 4 had extensions in order to make it compatible with IPv6. So we call it BGP4 Plus. All right. So BGP's main goal is to provide inter-domain routing in a way that guarantees loop-free routes. Okay. Before BGP was something called EGP. Okay, so there was an exterior gateway protocol actually called exterior gateway protocol. So back then, EGP was an EGP. All right, but now BGP has replaced EGP, and so BGP is the EGP of choice since EGP has been retired. So BGP has replaced EGP for the EGP. It is a classless routing. Okay, there's a bunch of CIDR blocks. And without CIDR, we'd have a whole heck of a lot of entries. Okay, and I just updated these numbers today. So right now there's 2.7 million RIB entries in the BGP table. And that went up by a couple 100,000 even since a year ago. Okay. So again, BGP is the only exterior routing protocol that we're looking at. Path vector, hierarchy required? No. It does not look at speed for the best path. It is a policy-based routing protocol. And as we get through these BGP chapters, it'll become clear what that means. But we use BGP attributes of each path to determine what is the best path. So routers are going to exchange what are called network reachability information, okay? And sometimes that's NRLI, network reachability, reachability. I don't know where the L comes from. And so this is, you know, what network is it? How is it reachable via what path? And what are the various attributes about that path? Okay. One of those attributes is a list of the AS numbers that path goes through. Okay. So when are we going to use BGP and when are we not going to use BGP? Okay. Well, first of all, whoever's implementing it needs to understand BGP and use it when there are certain conditions to use it. All right. One of which is the autonomous system is a transit autonomous system that allows other autonomous systems to reach each other through its own network. Okay, that is the definition of a service provider. So the other time you might want to use it is if your autonomous system has more than one path to the outside world. Okay. Another condition is the flow of traffic entering or exiting needs to be manipulated. You want to have some control over that. And so you want to be able to implement some sort of policy-based routing. Okay. When do you not want to use BGP? Well, if you have a single connection to the rest of the world, or if you don't really care about what routing policy or route selection you're going to use, or your routers can't handle the horsepower needed to manage the BGP updates. And of course, if you don't know what you're doing. A limited understanding, that's a nice way of putting it, about route filtering and BGP path selection. And then, of course, if you don't have a lot of bandwidth between autonomous systems, because BGP routing updates can be kind of big, right? The entire internet routing table is several hundred megabytes. All right. So you got to be able to send that across, and not only that, but parse it and whatnot. Okay. All right. So again, what is an autonomous system? A group of routers that, now in the context of BGP, that share similar routing policies within a single administrative domain. All right. So what does that mean? Maybe you're running a single interior gateway protocol, like a single company, or maybe you're running different protocols, but maybe belong to one organization. All right. But in either case, the outside world is going to view that autonomous system as a single entity. So that's one way of looking at it. All right. Now, these autonomous systems actually get official numbers assigned to them. Originally, they were all 16-bit numbers. All right, which means we've got 65,000 and change AS numbers available, with a small slice of them for private use, kind of like 1918 private IP addresses. All right. However, nowadays, in order to get an autonomous system, you have to provide a justification for it, and even still, you're probably not going to get a 16-bit number anymore. as it is. They've moved to 32-bit numbers. Okay. Um, if you uh, only have a single ISP and you still want to use BGP, IANA is not going to give you one. You're just going to use the private range. And then when your stuff gets out to the ISP, you're just going to get aggregated into their autonomous system number, and the private one's going to get removed. Um, and why would somebody want to do that? Well, maybe you want to get BGP set up because maybe you're in the process of getting another ISP, so you'll start with a private IP or private uh, autonomous system number, and then later on get one assigned. Okay, but if you only have one connection, IANA will not give you an autonomous system number. So nowadays I should update. I haven't updated this in a couple of years, but um, basically now you're going to get a 32-bit number autonomous system that we a lot of times will generally write as an IP address, just to make it easier. Although you could write it as a decimal number. Okay. Actually, no, that I updated that graph a year ago. I forgot to update it this year. Okay. So using BGP. So we're going to dynamically exchange routing information. We're going to be able to react to topology changes, including those changes that are happening far away. Okay. Now, obviously, connection redundancy is the main reason why we use BGP. Okay, so we can connect to a single ISP or to multiple ISPs. We've got these four different options here. Okay, the first one is we have a single homed autonomous system. One link per ISP, one ISP. One exit point to the outside network. So we're basically a stub network, right? So all we're really going to do is we are going to have a static route to the rest of the world. The ISP, I'm sorry, we're going to have a default route to the rest of the world. The ISP will have a static route to us, and we are definitely not going to need BGP in this case. Okay. We might possibly have our interior gateway protocol that we can kind of share routes with the service provider back and forth, okay? Instead of even bothering with BGP. So we would advertise our public network address, not private, but public, and we'll receive a default route, and we will coordinate that using an interior gateway routing protocol like OSPF, and then it would be the ISP's job to advertise our public networks via BGP. All right, so that's probably one way to do it where you're not messing with BGP because you only have one connection. The alternative is to do that same thing but use BGP. All right, but you're not going to get an autonomous system number. You're going to use one from the private pool, and then the provider will strip those off as you get advertised to the rest of the world via BGP. Okay. Dual homed, this is where you have two or more links per ISP, but still only one ISP, right? Here, both links are connecting to one device, and here, each link is connecting to a different device. All right. This is essentially the same as single homed, okay? But you do have some additional advantages, like you have primary backup link functionality, or maybe you're doing load balancing. You can do something like first hop redundancy or something like that. All right. But still, probably not going to be using BGP here. Then we get to single multi-homed, or sometimes just multi-homed. All right. One link per ISP, but multiple ISPs. This is definitely where you're in BGP territory. All right. Now, what are you going to learn via BGP from your service providers? Well, you've got different options. The first one is your ISPs will send you the full internet routing tables. You got to have some beefy hardware for that. The alternative is maybe full routes from one, partial updates from another, or default from one, partial updates from another. We'll talk about these different scenarios a little bit more later on. Okay. But one thing to keep in mind when it comes to receiving full internet routes, okay, actually, over 900,000 summarized routes. And I'm actually, I think Cisco has even upgraded this 4 gigs of RAM recommended. Okay. So if you don't have enough oomph in your router to handle the full routing updates, it may crash. Okay. Dual multi-homed. All right. So this is, multiple ISPs with multiple links to each ISP. Okay, so similar options to single multi-homed, same benefits, but with a lot more resiliency. Okay, so that brings us to the concept of aggregatable or non-aggregatable address space. Okay, so provider independent address space. That means your IPs are not going to be summarizable into your service providers. You're getting them from IANA directly, possibly, or from your regional registry, like Aaron in our case. Okay. However, if you're smaller and you don't have public your own address space, then you're probably going to get your address space assigned to you from your service provider, which means that address space that you're using is provider aggregatable. Okay, so your IP address that you get dynamically assigned to you at home. Well, that IP address belongs to your service provider and is aggregated into your service provider um, uh, paths or subnets, right? Advertised via BGP. Okay. So your provider independent address space is going to be address space that's assigned by the regional registry, unless you're getting it directly from IANA, which is unlikely. Okay. So when we're talking about IPv4, um, I'm sorry, IPv6. This is an IPv6 example. The regional registry might give you a /32, right? And that's common if you're a service provider or if you're a very large organization. So State Farm gets a /32. Okay. Um, so actually, you know what? I take that back. You pretty much get a /32. You get a smaller prefix if you're larger. Okay. So the nice thing about this is if you change providers, right, your network stays the same, and you can have multiple providers. Now, provider aggregatable address space means you're probably getting a /48. Okay, and then you got your subnet ID. You still have 16 bits for subnet IDs, which is still crazy large. Okay. You have to do prefix renumbering if you change service providers, although in IPv6 that is super easy if you do it right. One command can redo your entire network. It's really cool with IPv6. Okay, so we've got two different flavors of BGP. We have external BGP, eBGP, and that's when you've got BGP running and it's going between two routers that are in different autonomous systems. Okay, they're communicating with each other, but they view each other as outside of their own autonomous system. Okay, But sometimes you might have BGP running on routers inside of your own autonomous system, and they need to exchange routes with each other. That's internal BGP or iBGP. Okay. All right. So again, multi-home system, more than one exit outside of the network. Okay. So you might be a transit network, such as like a service provider, or a non-transit autonomous system, such as, you're a company that just has two connections to the rest of the world using two different service providers. What exactly is transit traffic that has a source and a destination outside of the autonomous system? So a transit autonomous system allows transit traffic, whereas a non-transit autonomous system does not allow transit traffic. Okay, so what does that mean? If you're a non-transit autonomous system, you only want to advertise your own routes to each provider. Okay, that way they understand that they can only get to those routes through you. You do not want to accidentally advertise routes learned from one provider to the other provider. Okay? Otherwise, that other provider might think, oh, I can get to that destination through your network. Okay? All right. So let's take a look at a couple scenarios. Our autonomous system is on the bottom there. It's 65,500, 65,500, okay, which is a private autonomous system number. We're learning routes from ISP A and B on either side there via eBGP. Okay, we're also running iBGP on our internal routers. We'll talk more about that later. So we are learning about routes to the rest of the world and choosing which exit out of our autonomous system makes the best sense. Okay. If one of those connections to one of the ISPs goes down, that's fine. All of our traffic will go the other way. No big deal. Okay. So we're basically using this as a way to set up a redundant connection to the internet, but we do not want to act as a transit autonomous system between our two ISPs, right? We don't want to act as a service provider. We're not a service provider. Our network is not for other people to use. Okay, so we're let's say we've got this network out here that's floating around somewhere else in the world. Okay, 172.16/16. Now that is a private network, probably not the best example, but pretend that's a public network reachable on the network. Okay. Oh wait, sorry, we're talking about that network. So this network 172.18 is actually let's say that's provider aggregatable to ISPA. Okay, so that's actually in the ISPA world. Okay, and so we're going to learn that from ISPA. Now, if we propagate that and advertise that out to ISPB, ISPB is going to say, oh, okay, you're advertising that to me. I know that I can get to 172.18 through your network. Okay, that would make our network a transit autonomous system. So obviously not a good situation. And if you don't know how to set up BGP, you could end up doing this very easily. Okay. So let's say we want to have our multi-homing setup. Okay, and we want to figure out what routes are we going to get from our service provider. There's those different combinations that we can do that I started to talk about earlier, right? One of which is we just get a default route from each service provider. Okay. And then, of course, in each case, we're advertising our own publicly routable IP space. Okay, we're advertising that. Or maybe we get a default route from each service provider plus the internet routes that belong to that service provider, right? So if some network was on the ISP1 network, if some prefix was on the ISP1 network, well then obviously the best way to get there is to go here. We wouldn't want to take that path. Okay, so essentially, if there's network X, ISP1 is going to advertise that plus a default route. And ISP2 will advertise network Y plus a default route. Okay. So if there's network Z out here, well, that's not being advertised to us. So we're just going to do a default route. We'll go that way or we'll go that way. But if we need to reach network X or network Y, then we'll go directly to that service provider. Okay. So this is a very common situation. We get a default route plus that service provider's routes. Okay. Or we're just going to go for the full gusto, and each one is going to give us full internet routes. Okay. So say we got network Z out here. Well, ISP1 figures out how it's going to get to Z. ISP2 figures out how it's going to get to Z. And we're going to make, we might go this way or we might go this way, all depending on, the path attributes. Okay. Whereas up here, if we're relying on the default route to get to here, this route might be better, but we might go that way because of the default route, right? So that middle option, we're not going to optimize routes necessarily. We're not going to take the absolute best path for routes that aren't part of ISP1 or 2. These default routes, we might not make the best situation. Okay. So in this example, we're just going to get a default route between each ISP. Okay. So we get that. We're going to propagate that default route into our routing, into our autonomous system via our interior routing protocol. Okay. This is going to involve the least amount of resources. This is going to be the least resource intensive. Okay. Our autonomous system is going to advertise its own globally routable networks via BGP to both ISPs. Okay. So if a router inside of our autonomous system, down there at the bottom with the question mark, learns about multiple default routes, well, the interior gateway protocol, the routing protocol inside of our autonomous system, it's one of those default routes, possibly both, will get installed. Okay, and we may end up with suboptimal routing. Okay, like we should have gone this way because this is connected, but we didn't. We happened to go that default route. So it's not that the packet won't reach there, it'll just be suboptimal. But using the default routes option from both service providers basically means we're okay with suboptimal. Okay? And we kind of have to be. Maybe we've got low end routers on our edge, and this is really our only option. Okay, we don't care which one we go out. We just want to make sure that people can reach our web servers that we're hosting. So we have BGP. Okay. Then we have the default routes plus the partial routing table from each service provider. Okay. So service ISP-A is going to give us ISP-A prefixes plus a default route. ISP-B is going to give us ISP-B prefixes plus a default route. Okay. Then we're going to advertise our internal globally routable routes. Okay. So our internal routers down here are going to receive these routes via our interior gateway routing protocol via redistribution. We generally don't redistribute BGP routes into a dynamic routing protocol. Although in this case we might if this isn't a lot of prefixes. Okay. So we will probably instead use an iBGP transit path, which we'll talk more about. Okay. So these interior routers are going to route packets, and essentially we're going to use ISP-A to get to ISP-A networks, ISP-B to get to ISP-B networks, and then default route to everything else, which again might mean we end up with some suboptimal routing perhaps. The other option is we get the full internet routing table from each provider. Okay. No default route now. And then we're going to advertise our own autonomous system routes. Okay. So we're going to have iBGP, so interior BGP, running on all the routers in the transit path. Now, I'm not saying we're a transit autonomous system. I'm saying whatever the transit path is between these two routers, all of those routers along that path are going to run iBGP. Okay, we'll talk more about that concept too. This is going to require the most resources, okay, because our routers have to process the full internet routing table from this side, the full internet routing table from this side. Okay. And so, if the full internet routing table is 300 megs, 400 megs, whatever, we have to parse 2 full copies of that and then figure out the which is the best route from each side. Okay. So our internal routers down here can get that again via redistribution. Full internet routing tables being, could you imagine the internet being redistributed into OSPF or EIGRP? Yeah, not going to work. Or via that iBGP transit path, which is what will happen. Okay. So the ISP that will end up getting used by any particular router will be determined by iBGP because that's the method that we're using. Okay. And so we can influence the path that we choose to certain networks. We can tweak it. We might not just leave it up to BGP, default methodology. Okay. So our router A and router B can make changes to the paths that get advertised into our network, and we'll talk about how that happens. Okay. So BGP path vector characteristics. Well, we know that we have different methods of calculating a metric, right? So OSPF uses cost, EIGRP, bandwidth, delay, reliability, load, RIP uses hop count. Okay, BGP looks at path attributes. Okay, one of those attributes is a list of the hop by hop autonomous system number that path represents. Okay, so for example, AS64700 on the right here. What networks can we reach there? Well, we've got those networks. Okay, so if we're somewhere and we need to get to that network, then what we do is we say we need to get to this autonomous system. How do we get there? Okay, well, we get there via this path. All right, now the path attributes will also include other things like the IP address of the next hop autonomous system, right? So the IP address of that router right there. How did the BGP universe learn about, the prefix or the subnet that we're trying to get to? Okay. And there's a whole bunch more too that we'll talk about. All right. So this AS path is used to create that loop-free aspect. We can tell if it's loop-free because if there's an autonomous system number listed twice that is not consecutive, consecutive autonomous system numbers are fine. We'll talk more about that. Okay. So, but in this case, you know, we're going to go to 64,520, then 64,600, then 64,700, and then of course to whatever the subnet is that we're trying to get to. Okay. No BGP router will accept a path that already has its own autonomous system number in it. Okay. And that's the same. So when you're talking about a routing protocol, doesn't matter what it is. OSPF, EIGRP, RIP, BGP. How you prevent loops is each router makes sure, you know, like this is a loop. Each router makes sure that itself is not at the cross point. You know, this router can't prevent that loop. The only router that can prevent that loop is this one. Okay. Well, in this case, we're dealing in, you know, autonomous system numbers or autonomous systems. Of course, the loop prevention mechanism here is the path attribute. Okay. So here we have a network. Okay. So we have 172.16/16 that is getting advertised. And as that path gets advertised, or as the path gets advertised, the path attributes, the AS path attribute is updated as it kind of propagates along. Okay, so in this case, Autonomous System 7 here knows that it can get to that autonomous system in the lower right by going through Autonomous 4, then Autonomous System 2, then AS1. All right. So what it's going to do is it's going to advertise that to its neighbors. Okay. So AS7. So right now the path is 421. Right. It's going to advertise that up to Autonomous System 8, 9, and then it's gonna come back around. But notice it goes 421, then 7421, then 87421. Okay, and now it comes back around to 7. But notice the path is now 987421. Okay. Autonomous System 7 sees the 7 in that path and says, that would create a loop through me. Not going to do that. It will not accept that path. Okay. So in this scenario, how many possibilities do we have to get over here? We're going to start here. We're going to get here, and we're going to go through that as our next hop. Okay. Well, here's one path. Okay. Here's another path. Here's another path. And of course, here's another path. However, this autonomous system over here does not see all of those paths. Because if it did, that would be like saying each autonomous system sees every possible path to every possible destination on the planet. Clearly, that's not going to work. Okay. But no, what it's going to see is this autonomous system is going to pick its own best path that it likes, and that's the path that's going to get advertised. So the autonomous system on the left there is only going to see one path advertised by that autonomous system. And then the same thing goes with its other autonomous system neighbor. It's going to advertise its best path. So we essentially have two choices. Okay. We can, and it's just like our interior routing protocols. Each router chooses which next hop to go to. Okay. It's the same thing, except the next hop is just on a bigger scale. Okay. So this decides if I'm going to get here, do I go here or do I go here? And that's based on what each one of these has advertised. Okay. All right. So again, kind of harping on the transit autonomous system issue a little bit, but it's a major issue. Okay. Your incoming route advertisements are going to influence your outgoing traffic. Does that make sense? Okay. If there's a network out here, that is going to get advertised incoming, which is going to affect my outgoing traffic. How do I get there? Okay. And our outgoing advertisements, so what we are advertising, is going to influence the incoming traffic. Okay. So ISP1 says, here are the networks that you can reach through me. ISP2 says, here are the networks you can reach through me. And this one says, I will try and make it so that you prefer me. Our router says, okay, we have a choice of which way to go, which way to send our traffic. Okay. All right. So we are also going to advertise our networks to the outside world. So our router talks to ISP1 and says, these are the networks you can reach through me, but I am not going to include ISP2 networks. Okay. ISP2 says, these are the networks you can reach through me. I will include ISP1 networks, but I will include my autonomous system number multiple times, so you may prefer another route. So we'll talk more about that concept here. That's called AS path prepending. Okay. So let's say we inadvertently advertise ISP1 routes to ISP2. We're not doing any AS path prepending or anything like that. That's a total accident. Okay, ISP2 customers on the right will see our network, potentially, as the best path to ISP1 customers. Okay, that's going to make us a transit domain. Now, there's lots of ways that we can do to prevent that. Okay, we will get into those when we get into the actual configuration and route filtering and things like that. All right. When it comes to working with other routers, okay, we are going to peer with them. We're going to create a peering relationship. You know, similar to EIGRP or OSPF, right? Except the difference is when we're talking OSPF or we're talking EIGRP and we're making the two routers peer together or create an adjacency in those protocols. The difference is we are in control of both of the routers. Here with BGP, you know, different people are in charge of the two different routers that are wanting to peer together. Okay, so we end up with, we have to trust the other side, but we have to also understand that they could screw things up. Okay, so you on the one hand, you got to trust that the other network administrator knows what the heck they're doing. On the other side, you're going to take whatever steps you can to prevent their mistakes from hurting you. Okay, so paranoia is your friend. Not out to get you doesn't mean they're not going to try and get you. Okay, they may do it accidentally. Also, if you make a mistake, you could cause problems for somebody else. Okay, if you advertise a prefix that you don't actually own, then the rest of the internet might try to use you to get to it. Okay, this particular network belongs to Microsoft, and you've just advertised to the world that you have it. All right, so they may send packets your way only to get, black holed. You're going to get flooded with traffic that you probably can't handle. Microsoft and your service provider are not going to be happy. This next section that we talk about is where the internet was kind of taken over a little bit. So we will watch a video really quick, and then I'll talk about what happens. Let me know if you can't hear the video when it comes on.
Check out this Verbo.
Oh, man.
Michael, they're your cousins.
The RIPE NCC operates 14 route collectors worldwide. These collectors receive BGP updates from almost 300 peers. Let us look at what the RIPE NCC Routing Information Service saw of the recent unauthorized...
You can hear it, JB, but it's not showing on the screen.
This is BGP, a tool developed by Roma Tre University in Italy in close cooperation with the RIPE NCC. BGP updates from almost 300 peers. Let us look at what the RIPE NCC Routing Information Service saw of the recent unauthorized route announcement affecting YouTube. This is BGP, a tool developed by Roma Tre University in Italy in close cooperation with the RIPE NCC. The red circle at the bottom right represents Pakistan Telecom's autonomous system number 17557, and the red circle on the bottom left, the YouTube autonomous system 36561. On February 24th, at 1847 UTC, Pakistan Telecom started to originate a /24 covering address space assigned to YouTube. We can see that this route spread rapidly in the part of the internet observed by the RIPE NCC Routing Information Service. Within roughly a minute, the route is visible at most of the autonomous systems shown in this animation, and traffic starts to flow towards Pakistan. "17 minutes later, at 20:07, YouTube starts to announce the same route itself in order to route the traffic back to its own servers. Another 10 minutes later, around 2017 UTC, routing policy changes occur that move traffic for this route away from Pakistan Telecom's upstream PCCW AS3491. Another 20 minutes later, Pakistan Telecom's autonomous system number is repeated in those routes announced by AS3491 in order to make them less preferable. Another 8 minutes later, the unauthorized announcements are no longer propagated, and both routing and traffic revert to YouTube at around 21:03 UTC. These animations and many other tools are publicly available at riz.ripe.net. There are also prototypes of new services.
Well, let me draw a picture. Okay, so over here, Pakistan Telecom, this is their upstream PCCW Global. That's their service provider. Okay, this is YouTube, youtube.com, AS36561. Okay, all right. So essentially, if we were to, youtube.com, that's going to resolve to this particular subnet in this example. All right. So we have these three /24s. Those /24s are going to be summarized into a single /22. Okay. So all three of these are advertised as the 208.65.152/22. And so YouTube advertises that around, okay? And now, Pakistan Telecom is essentially 4 hops away, okay? But Pakistan Telecom doesn't want YouTube viewable by their customers, we'll call them. And so it's going to block traffic from inside of its autonomous system from going to YouTube. We're not totally sure exactly the technicalities of how they did this, but we can see the effects of this because, they essentially want that to get black holed, okay? So what we think is they created a rule here that sent traffic to a non-existent network, okay? But they then propagated that path to their upstream provider, which then advertised that route to everybody else, okay? So now this /24 is being advertised. The upstream provider shares that, okay? Now, what do you notice? The one that they advertised is more specific, okay? So that means if you're trying to get to this subnet, right? Everybody in the world, no matter, you could be right next to YouTube servers, and if you're trying to get to that 153 subnet, you're going over here because YouTube is not advertising the 153 subnet. They're advertising a /22, and a /24 is more specific. That means Pakistan Telecom is basically stealing all the traffic for that subnet. Okay. So, for example, this router gets a packet to the 153 subnet. Which way is it going to go? Well, it's going to go to Pakistan because the /24 is more specific than the /22, right? 24 bits is a longer match or a better match than 22 bits. Okay. So, announcing that same /24. All right. Now it's going to be all about hop count for the most part. So if you're closer to this side, you'll go over here. If you're closer to this side, you'll go over to here for that /24. So that kind of helps, but some traffic is still going the wrong way. Okay. So then YouTube starts advertising even more specific. So they break that /24 into 2 /25s. So now they're basically taking it all back. Okay. And then finally, PCCW, the video said they did some AS path prepending, but even that didn't work. They stopped accepting routes from Pakistan Telecom. They just said, nope, you're done. So what PCCW Global could have done, now you don't do this as a matter of practice because it defeats the point of having BGP and routability but what PCCW Global could have done is prevented Pakistan Telecom from advertising any routes that didn't belong to Pakistan Telecom. Now, on the surface of it, you might say, well, yeah, they should do that anyway. Well, not necessarily, because maybe some major networks go down and we need to route traffic through Pakistan to get to someplace. Okay, if we only allowed Pakistan to advertise their own prefixes, we could never use them as a transit autonomous system. And service providers need to be used as transit autonomous systems. That's what they're for, right? Okay. So there you go. And a few years prior to that, the same thing happened where traffic that was owned by the U.S. military was routed through China. The official story is that was an accident. Who knows? All right, back to BGP. So BGP uses TCP. Okay, that means you got to be able to ping the other side. You got to be able to route to your this router has to be able to ping that router. So routing is already going on somehow. All right. So it's TCP port 179. RIP uses UDP. EIGRP uses its own proprietary RTP, Reliable Transport Protocol. OSPF has its own little thing also. Okay. But BGP, we have to have connectivity between the two peers before BGP is even running. Okay. And TCP must be negotiated. All right. The nice thing about the fact that BGP uses TCP is we get those TCP benefits, like reliable connections. Okay. Flow control, like the sliding windows. Okay. Since BGP understands that we have that reliability mechanism from TCP, BGP doesn't handle that. Okay. There are no if EIGRP or OSPF gets an update, they acknowledge the update. Okay. BGP doesn't mess with that because TCP handles all that. So we have neighbors or peers that are going to connect to each other. They're going to create a TCP connection between each other. Okay. BGP speaker is a router running BGP. All right. It has a limited number of BGP neighbors, and that's just another way of saying it will only create BGP relationships with other routers that you explicitly configure. There's no discovering neighbors automatically with BGP. You have to configure it. So both sides have to be manually configured. If only one side is configured, you're not going to get a BGP relationship. Okay. So again, these peers can be internal to the autonomous system or external to the autonomous system. That's the whole IBGP, internal, or eBGP, external. Okay. So we've got external here, right? This is an autonomous system 100. This is an autonomous system 200. Okay. They're usually directly connected. That means they're going to be like one hop away. But we'll talk more about that later. Okay. eBGP relationships means that they are in different autonomous systems. They have different autonomous system numbers. Okay. So like I said before, you have to define the neighbor in the configuration. So we have a neighbor command. Okay. So you need to, like, a good test is, can you ping the neighbor? All right. So when we get into BGP configuration mode, we say router BGP and then the autonomous system number. Okay. So we've got router A here, router B here. Router A is an autonomous system 100, B is in 200. Okay, that means they're going to be in, eBGP relationship. Okay. Now, unlike the other routing protocols that we've messed with, you can only have one BGP process running at a time. That means a router can only belong to a single autonomous system or have a single autonomous system number for BGP. Okay. Now, since these two are configured with different autonomous system numbers, they're going to connect up with an eBGP relationship. And this is what it looks like. We have the neighbor command. Okay. And we have the IP address of the neighbor, and then we tell it what the autonomous system number is of that other neighbor. Okay. So that's going to determine if it's eBGP or iBGP. Okay. So here it's eBGP, right? Because 100 is different than 200. Now, when we look at iBGP, where the routers are inside the same autonomous system, then the numbers are going to be the same. Okay? And why would you do that? Because we need to exchange BGP information. We have that internal BGP path that we can use to propagate BGP paths within our network. Okay, and this is usually going to be done on a full mesh basis. Not full mesh as far as your network goes, full mesh as far as the routers. And so we'll talk more about that here coming up. Okay, so again, it's iBGP, so it's going to have the same autonomous system number between the neighbors. Okay, we're still going to use that same neighbor command. All right, and we still need to be able to have TCP connectivity. Now here, it's less. Well, they don't have to be directly connected. Okay. So here we can see the neighbor commands. They're in the same. The neighbor is in the same autonomous system as that router. So it's iBGP. Okay. So here we can see the BGP transit path. All right. We have, in this example, we have a neighbor relationship between B and E, but no neighbor relationship with D and C. Okay. So the transit path is the red arrow or the blue arrow. Okay. Even though B and E have a adjacent, well, you can't really say adjacency because they're not adjacent, but they have an iBGP relationship. Okay. So we're going to use that transit path to propagate BGP advertisements within our own network and possibly out the other side. Okay. The other way of doing it is, instead of doing that, is to redistribute the BGP routes into our interior routing protocol, but that's generally not done, especially if you're using full internet routing tables. Okay, so BGP was originally designed to run along the border of an autonomous system. Okay, being totally unaware of that. Okay, and that has implications for a transit autonomous system, which are usually service providers. Okay. So all routers in the transit path have to know about all those routes. Okay. Again, two options to accomplish that: run iBGP on those routers, or redistribute those BGP routes into the interior routing protocol. Okay. All right. So iBGP in a non-transit autonomous system. So we're multi-homing. We've got two autonomous systems. Okay. But we are not going to advertise routes from one ISP to another. Okay, so that is what the scenario is. Okay, now the next slide or two might be a little hard to understand, but stick with me; it'll make sense. Okay, so the designers of BGP couldn't guarantee, they have no way to make sure that an autonomous system would run BGP on all of its routers. Okay, so there had to be a method to make sure that iBGP routers could pass updates to each other without creating loops inside. Right, the BGP protocol can prevent loops on an autonomous by autonomous basis, but not inside of an autonomous system itself. Okay, so the method that they chose is they basically said all iBGP routers in the transit path have to peer with each other. Okay, and then there's another step which I'll tell you in just a second. All right, then routes that are learned via iBGP are never learned via iBGP to another neighbor. Okay, I know what you're saying, that makes absolutely no sense. It will. Okay. So that means each iBGP neighbor has a neighbor statement for all of the others. Okay. So here's like, we have eBGP relationship to each one of these. Okay. So let's say an advertisement is sent eBGP. Okay. Then that gets sent via iBGP, but this one will not send that via iBGP. Okay, no, it must be full mesh. This one must send that via iBGP to the other neighbor. Okay, so when this neighbor learned it via iBGP, it will not then advertise it via iBGP. Okay, the only way you can advertise something via iBGP is if you learned it via eBGP, which means all of the iBGP neighbors have to be fully meshed so that if any one of them gets an eBGP advertisement, it can fully mesh, send that to the others. Okay, so again, the internal network isn't fully meshed. It's just all of your iBGP routers are fully meshed to each other. Okay. So again, no iBGP advertisement of that. Okay. Okay. Let's see what happens if we have a partially meshed situation. Okay. So we have our autonomous system here. We've got AS 65101, 65103. Okay. So this is essentially 1, 2, and 3, right? At the end of the autonomous system number. All right. So router B is going to receive a BGP update from router A. Router B has two iBGP neighbors, routers C and D. Okay. Router B does not have an iBGP neighbor with router E on the right of our network. Okay. So C and D are going to learn about the networks from router B. Okay. Router C and D have iBGP relationships with router E, but they are not going to send the updates from B, because remember what we just talked about. Okay. So sending the iBGP update to router E should be router B's responsibility. Okay. Which basically means router E is not going to learn about any networks from B because it doesn't have any relationship, which means router E is never going to learn about these networks and it's not going to be able to advertise those if we want it to. Okay. Full mesh though, so we've got a neighbor statement pointing here, a neighbor statement pointing here, and a neighbor statement pointing here. Keep in mind, the B and E are not directly connected, but because of our interior routing protocol, B can ping E. Okay? So that means we get an update. B is going to advertise that to all of the iBGP neighbors because all of our iBGP neighbors are fully meshed. Okay? Again, keep in mind, this is, let's say this is the physical, those are the physical wires. The network is not fully meshed, but the iBGP neighbors are fully meshed because B has a relationship going here. The actual packets might go here or here. That's fine. It's just a packet that it's a TCP segment that's put in a packet that the destination is here. Does everybody kind of understand the distinction I'm making? It's not necessarily a fully meshed network, but the iBGP relationships are fully meshed. And that's fine because we can route those packets. Like we could have a network like this. Right? But our TCP, our BGP is like this. This is kind of an extreme example. So that is the network statements from here. But then, of course, we also want okay. So in red are the physical cables, but in purple are the neighbor statements. So in this case, they're all fully meshed as far as BGP is concerned, IBGP, okay? But the physical network isn't fully meshed or anything. So again, I'm not saying the physical network is fully meshed. I'm talking about the IBGP relationships, right? Because if we want to send an update from here to here, that's the relationship, but the packet itself, is going to go across the physical wires until it gets there. Okay, does that make sense? Y'all picking up what I'm putting down? You buying what I'm selling? You eating what I'm feeding you? Okay, so back to the scenario, okay? B learns an update from A. B updates all of the IBGP peers, router C, D, and E. Okay. The interior routing protocol, whether it be OSPF or EIGRP or whatever, that's going to be used to route those TCP segments containing the BGP update from B to E, like I just was explaining. Okay, because those two routers are not actually directly connected. They're not physically fully meshed. Okay. And of course, these IBGP updates are not propagated again via IBGP. Okay. So this is going to reduce unnecessary traffic. All right. And all of these other routers they're assuming all the others are fully meshed. Okay, that's the assumption. Okay. What happens if we're not fully meshed? Okay. So here we have a BGP relationship between B and A, an IBGP relationship between B and E. Router E has an eBGP relationship between E and F. Okay? And an IBGP relationship between itself and router B. C and D are not running BGP, okay? But we are running OSPF in the domain, okay? So a network gets advertised. So router B learns about the 10 dot network, okay? Router B is going to advertise that via IBGP to router E. So that works, okay? The TCP segment is able to get there because, we're going to use our interior routing protocol, and that advertisement is going to go one of two ways, but it's going to get to E. So, but of course that TCP segment is passing through C or D, but C or D, they're not looking at the packet, they're just routing it. Okay, so C and D never learn about the 10 dot network because, again, BGP is not being redistributed into OSPF, and that's all they're running. C and D are not running BGP. Okay, so then router E is going to advertise that to F. So it learned it via IBGP, but because router F is an eBGP relationship, it'll advertise it around or advertise it out. Okay, we haven't told it not to, and we'll talk about how to do that later. All right, so basically, A, B, E, and F all know about the 10 dot network. Okay, D and C don't. Okay, so if router F has a packet for the 10 dot network, it's going to send it to router E because that's, it learned about it from there. Okay, router E would then send the packets to its BGP peer, router B. Okay, but of course, to get to router B, it's either got to go through C or D. Okay, let's say it goes through C. Okay, but C and D do not know about the 10 dot network, so it's not in their routing tables. Okay, So when this gets packeted to either C or D, it doesn't have a destination for that, so it's going to get tossed. All right? Well, default route. Okay, well, let's say there is a default route. Okay, let's say the default route's going the wrong way. Okay? Well, then we might have a routing loop situation where C keeps sending it to E and E keeps sending it back to C. Okay? So, to get around this type of problem, BGP needs to be implemented on all the routers in the transit path. Okay? That means C and D in this case. So, then that begs the question, can BGP help ensure that all the routers in an autonomous system know about these external networks in other ASs? That brings us to BGP synchronization. Okay? So, notice we have A and B that are peers. I'm going to change the color of this. Red's a little bit easier to see. Come on. Okay, A and B. Okay, they are not directly connected. All right, they have a BGP relationship, but they're not directly connected. Everything has to go that way. Okay, so BGP synchronization says that we should not advertise to an eBGP neighbor a route learned via iBGP unless that route is directly connected or learned from the interior routing protocol. Stick with me. Okay, so what does that mean? So we're going to advertise that network. Okay, so should A advertise that to E? Well, A says, I learned about the 172, so eBGP, iBGP, and then do we advertise that? Okay, so router A says, I learned about the 172.16 via iBGP, but should I advertise it to router E? Well, I'm not going to, because I learned about it via iBGP, and yet it is not in my IGP routing table, right? OSPF doesn't know about it. Okay. Now, in the past, this used to be the default. Okay. But that was when we could redistribute all of the BGP routes into the interior routing protocol. And then that would get advertised to all of our routers. Okay, so in this case, C and D would know about that network. Okay, and we would not have to have iBGP running on all of the routers in the transit path. Okay, because here's the transit path, right? Because these are not directly connected. Okay, so before we just assumed we would learn about all of our eBGP routes. We would redistribute those into OSPF, and then all of the routers would know about it. Okay, and if all the routers know about it, A knows, hey, if I get a packet, I know it'll make its way around. As long as OSPF sees that, I can advertise it out because I know my network can handle it. Okay? That's synchronization. All right. I just explained this whole slide already. So C and D have to know about the prefixes that we're advertising, right? Because if we get a packet, C and D have to be able to route those. Okay? What about no synchronization? Okay? We cannot redistribute BGP networks into the interior routing protocol. There's just too many of them. Okay? Instead, we need to make sure that all the routers in the transit path run iBGP. Okay? So this one and this one, because this is the transit path. All right. So IBGP, and of course they all have to be fully meshed with each other. Okay. So synchronization is disabled by default nowadays, which means you have to run IBGP on all of these routers. Okay. So now we can advertise this route. You know, A can advertise that route via eBGP that it learned via IBGP because it knows, or it's assuming, that we have IBGP running on the transit path. Okay. And again, these are fully meshed. Okay, it's not clearing. Let me jump to the correct slide here.
JB, what do you mean by fully meshed?
So fully meshed means, so this one, actually, my clicker, there we go, now it's working. Okay, so if we look at router B, okay, it has an eBGP neighbor statement to F, okay, but fully meshed is IBGP. So router B has a neighbor statement to A, it has a neighbor statement to D, and it has a neighbor statement to C, okay? So if it learns about a path via eBGP, it'll advertise that to all of them, all right? Router D has a neighbor statement to B, a neighbor statement to C, and a neighbor statement to A, okay? And then router C has a neighbor statement to B, a neighbor statement to D, and a neighbor statement to A. And then A has a neighbor statement to B, D, and C, okay? So each one of them have a neighbor statement to all of the others. So even though they aren't physically wired together, like there's no direct connection between B and C, but there is a neighbor statement, okay? Which means it has an IBGP peering relationship with C. So when it learns about a prefix via eBGP, it's going to send that via IBGP to C. And then of course it's going to send it here and it's going to send it here. Okay? So being fully meshed means that whenever an advertisement hits a edge router via an eBGP relationship, it's going to propagate that to all of the IBGP neighbors, whether it's directly connected or not, physically. Okay, does that make sense? Does that help answer your question?
Yeah, it does.
Okay.
So maybe in this case, like do we have OSPF also on all of them, and then IBGP also?
Yes.
Okay.
Yep. Because so we have a neighbor statement from B to C, let's say. Okay, so B and C are not directly connected, but B gets the advertisement here via eBGP and needs to send that to C. Okay, all right. So how does it do that? Well, it's got to be routed through the network. So let's say router C is 1.2.3.4. Okay. And so router B needs to send that advertisement to 1.2.3.4. It then has to look in its routing table and say, how do I get to 1.2.3.4? Well, it's only going to learn about that because of OSPF. So you can think of it like this. Before this BGP connection is going to work, we have to be able to ping router C. We have to have TCP connectivity. Router C has to be in B's routing table. And so OSPF is going to handle that for us. Does that make sense?
Yeah, so in this case, like the IBGP will be the payload.
Exactly. Yep. Yep.
Okay.
Well, apparently my cat's telling me that we're done. And we are. Okay. So that was a, quick introduction. Okay. Now the cat's like hitting buttons and things. All right. So any other questions or anything? And a lot of this, it'll start to make sense too once you start working with it in the labs. And also, kind of as we go around the next thing. Just remember, in the old days, the internet was not huge. We could redistribute the internet routes into our interior routing protocol. That means we could route whatever we wanted wherever because all of our routers knew about all of the destinations. Okay. When we stopped being able to redistribute the internet into our routing tables, then we had a problem with our all of the routers in our network did not know all of the internet's prefixes. Okay. So we had to have BGP running on all of the routers that represent the path that it would take when something comes into our network and goes out of our network. What is that path? So basically all the routers on the edge of our network, essentially. Okay. All right.